Welcome to this recorded video that will go over the solutions to some of the activities in the Part B lecture notebook for the fourth module on integration. The fourth module is on computational applications, and this particular Part B lecture notebook is on integration. So the first activity is on rectangle rules. And again, you should feel free to create many new code and markdown cells below as you work through this activity. That's a just general instruction that applies to all activities. I ask you first to create a wrapper function called multiple rect approx with underscores. So the first thing you should do if you're reading that is just say, okay, definition, multiple rect approx, with some parentheses for where the parameters should go because it's a function. Or, if it doesn't have any parameters, it's that. And then the colon, of course. And then you go ahead and press enter and create the indenting. Now, what's the next part of the instructions? It has all the same parameters as compute rectangle rules, compute rect rules, except that the in parameter is now assumed to be an array or list of integers containing different numbers of rectangles for which the approximate integral should be computed. Okay, has all the same parameters as compute rectangle rules. So let's go look at the parameters for compute rectangle rules. We scroll up to where I define this function right here in the lecture notebook, compute rectangle rules, and it has 5 parameters that we see here. We see that it has f, which is a function to be approximately integrated, a and b, which is the interval on which to integrate this function, n, which is the number of rectangles to use in the approximation, and then a rule that has a default value of left for the left-hand rule, and you can then choose, of course, right or anything else, which would give you the midpoint rule. So I'm just going to copy those parameters, and then immediately go down to, sorry for all the scrolling, here, and put it in. So now that has accomplished at least the first sentence of instructions that we've created a wrapper function called multiple rectangle rules. It has all the same parameters as compute rectangle rules, and except we're just going to interpret n differently. Now, what should this wrapper function actually do? It should loop through all the values in the list of n values, and it should then call the compute rectangle rules to obtain the associated approximate integral, and it should store all of the approximate integrals in a list that is returned by the wrapper function. So I would say, okay, I need to then create a list that I append each value of the list with the output of the compute rectangle rules that gives me the approximate integral. That's what I want. So the first thing I'm going to do is create a list of approximate integrals. So my approximate integrals, approx_int, will be an empty list. Now, of course, I'm just showing the code. You should always have, I say, just as good practice, you should probably put a useful doc string here and, a useful doc test or two as well. I mean, you should have these things as matters of practice, but I'm, for the, purposes of these videos just showing the coding portion, I'm going to just show the code, but I don't want to make it seem like the doc strings and the doc test and code comments, those are all really useful and you should be doing them, but I'm trying to keep these videos kind of tight. So, all right, we now have this empty list. We want to loop through all the values in this array of n values or a list, whatever it is, that should be integers. And that's another thing to maybe check. You could do type checking with isInstance and all these other things. Those are good things to do. I'm not doing them all the time because it depends on the focus of the code. But it's a good thing to just do. If you do it, it's great. I highly encourage you to do it. So anyways, I want to loop through all the n's for the n's in n. Let's do it like that. So for each of the n's in n, then what do I need to do? I need to compute the associated rectangle rule with that particular n's value that's in this array of n's, and I need to store the result in approx_ints. The simplest way that I can think to do that is to just append that list with exactly the output of the compute rectangle rules I want. So let's look above to, and I think I've done something similar to this. For instance, like here's my int approxes. I did something similar where I was computing rectangle rules with a function. So it's very much like this. And you notice I have these 3 outputs. This is all, basically coming from the lecture notebook. If we look at this function though, just as a refresher, it returns, this compute rectangle rules returns the ix and iy values, which are the indices Well, they're not exactly the indices. They're what are used for the integration x and the integration y values, and they're useful for for producing the plots of the rectangles in some of the plotting results I show below. And delta x is just something that's related to the width of each of the rectangles, the length of the base, or you could also call that the width. I really want this fourth entry, which is then, because of Python indexing by 0, given by 3 when I index the outputs. And that's why you see this output here. That's just a refresher. I know I talked about that also in the lecture notebook. So pretty much, I just want to do this. I want to call the compute rectangle rules. I want to pass it the f, the a, the b, and the ins value, because that's what I'm looping through here. And I also want to pass it the rule, because, you know, I can call a multiple rectangle approximation different rules, and it should pass that to here. And then I just want the third output of that function for that particular ins value, and that will give me the approximate ins. And you could change these variable names to things like I did above. I, you know, created the lecture notebook, you know, months ago, and now I'm creating this solution video, and I didn't really review the lecture when I started creating this. So these variable names are arbitrary. You probably use what I did in the lecture notebook for consistency. But at any rate, I then ask you to return, right? Store all of the approximate integrals in a list that is returned by the wrapper function. So this is a function that just wraps around compute rectangle rules. Its whole purpose of existence is just to call this function multiple times and store all the multiple outputs in a list. And we do that with the append, and then we return it. So as far as the code goes, this is the level of complexity of this function. It's a nice simple wrapper function. Run it, we create it, that's it. We've completed the first part of this activity. Now, the second part is for a number of different lambda functions, including f of x equals x, that's basically what this is, f of x equals x squared, and at least one of your choosing, maybe you choose x cubed, maybe you choose something more interesting than a monomial. You should then also compute the errors for the left, right, and midpoint rule approximations for n equal 10, 100, and 1,000, right? So I will be calling the multiple rectangle rules with that list of n values and integrating over 0 to 1 for a and b. And I will store the errors as either a list or NumPy array. I give a hint here, which is to compute the errors, you need to either know the exact value or a very accurate approximation of the integral of the function to compare the rectangle rule approximations. Use the imported quad function from SciPy integrate as to obtain, I should say, the exact value. It is a very good approximation, at least in almost all cases. I really was doing this above. If you were just following along what I was doing in this code, like if you come to here, I was creating these integral approximations. I was appending, right? I created this empty list. I just basically took this code and with slightly different notation or variable choices. This is what's in the multiple rectangle approximations code I just defined in the activity. And then what I did is after I, computed these integral approximations, is I cast that list as an array. And I subtracted by this because, right, I need to actually subtract from every component in the list. And in order to do that, I need to turn that list into an array. And then I subtract off basically the integral, or at least as accurate approximation as is necessary, which is obtained with the quad function, which we've imported above. And then I create that, what is now an array of errors, and then I would compute these error approximations. And this would just be for one of the rules. So I'm going to do something very similar. I am going to, scroll down too far. For, let's say, f equals lambda x, I'm going to go ahead and say, like, you should do it for the f of x equals x, well, I'll do it for f of x equals x, because that makes a good point, actually. F of x equals x, I'll do that one. And so I've created that lambda function, and now what I'm going to do is I'm going to have if I'm going to return a list here, I want to call this with the different rules. And I could say, let's say, errors, for, we'll just call them, we'll just say errors left, that it was going to be for this function. In fact, I'm going to do this all in one code cell just to give you this sense of how compact all this code is. So I am going to call this function multiple rectangle rules. I just press tab so it does the autocomplete. I'm going to pass the f. There's only one f defined here, so I can say f equals f, but I could just pass it here. It just makes it a little bit more explicit. You could also just put that lambda function like right here as the first argument. I'm just doing it a little bit less efficiently because I think it adds, in this case, a little more clarity to what's going on in the examples. And because I'm also going to use this f in multiple places. So I actually do want to define that lambda function as a variable since it's referenced in a few places. I'm going to integrate from a equals 0 to b equals 1. I'm going to use the rule left because I have left here. Now this returns a list of approx ints. I want to cast that output that's returned by that as an array. I want to subtract off now using the quad function the integral of f from a equals 0 to b equals 1. And you can just go back and check how I was using the quad function above to do something similar. Quad f, you give it an a, you give it a b, and then you only want the integral approximation. So that's the first component returned by this function. It returns a couple things. I talked about that in the lecture notebook. But let's go ahead and return the 0. And now that will give me the errors left. I can then make an errors right, and then check this out. This is very simple. Because I'm using that same function f, I'm going to make, now the only difference here is this rule is the right-hand rule. Oops, I did press the delete key. And then I am going to also do errors, let's say mid for the midpoint rule. Same thing, except I changed the rule here to mid. If I run this now, hopefully I don't get any errors. I got a type error, so let's see if I can do this. Well, of silly me, I did not pass the in. I didn't pass the in here. I was just being silly. And that was because I was following, I think, the idea of something else. Well, I'll fix that right here. For all the examples, so I'll put this in its own code cell, I will create this list of 10, 100, and 1000. And there we go. Now I will pass that into each of these. It's nice to see an error every once in a while and how I fix it. You don't get flustered. You just kind of try to look at what was going on. Right? It's very simple. So the type error, you're missing a n. It told me exactly what was wrong. Now let me run it. Positional argument following a keyword. Oh, here we go. N equals n because I was started to keyword these and then you didn't keyword, right? So another error. That's a syntax error. Positional argument cannot follow a keyword argument. We remember that from, hopefully we remember that from module 3. So there we go. The n is equal to n in this case with this array of n's. So I could get rid of the whole thing by just making that 0 and 1, but I like the a equals 0 and b equals 1. All right, now let's run it. Great, no errors. Now, I have these errors. That's it. I store the errors as either a list or array. Notice I'm not saying to do any analysis of this yet. So I want to do this for each of these different functions. And in that case, maybe I would say maybe you want to call this like, if this is your first function, this might be, let's add a 1 to each of these. So you kind of can systematically come through and change all of these. So this is the first set of errors that you compute. All right. And then you can change your f. This keeps the code simple. Make these 2's now. I don't have to change so much. This is now the x squared. Okay. So here I am integrating the function f of x equals x. Here I'm integrating the function f of x equals x squared. And that f is now being used in all these places when I define it here. And I'm getting the second set of errors. And then you can create, let's say, your third set of errors here. Let's say x cubed, whatever. You could do one of these like cosine of x cubed minus x, minus 2x, like something we used from the roots function or some other complicated function. It's up to you. You don't have to make it too complicated. It just has to be something different. So this is my third set of errors that I'm computing. And if I run each of these, there we go. That's it. For a number of different lambda functions, including f of x equals x, f of x equals x squared, and at least one of your choosing. So choose something else. You could choose x cubed if you want, but I encourage you to try something else. And you can definitely do more as well. You've now completed the second part of this activity. That's kind of all there is to it. We're just calling the multiple rect approximation. We're casting that list as an array so that we can do an element-wise computation of subtracting off the integral from each one. And now we have these errors. Now, for each of the different lambda functions we've computed above, we want to create a log-log plot with a legend that shows the errors for each rectangle rule approximation versus the number of rectangles. A log-log plot of errors is useful for analyzing the rate of convergence of a method. We like to see the errors decrease as we increase the computational effort, meaning we use more rectangles. The n value is higher. We want to estimate the rate of convergence using the np.polyfit function as shown in the example above, which means above this activity. And I say again, a hint to use a log-log plot, everything must be non-negative. So you should be using an np.abs function on the y values of this plot, meaning the errors, because the errors can be positive or negative. We just care about the magnitude of the errors. And again, this is as shown above. So as shown above, let me just show you exactly where this is above. Like here. Here's this type of visualization. I can just go ahead and copy this. I'll do this for the f of x equals x. We'll also estimate the rate of convergence. We'll do all of this. So first, for the first figure, I am going to have the errors left 1, right? Because remember, I have errors left 1, errors right 1, errors mid 1. I would put all of these on the same plot. I would label this with left, and then I would copy and paste with, and this is right, and this is mid, so you can see what I'm changing. And then of course change the labels, so you shouldn't label everything the same because that makes no sense. Right, and mid, and then we're doing this for all of them, so let's update this, and it's for f of x equals x. We'll put that in $signs because we want to render the tech. And we will create a, so we have the x label, we have the absolute value of the errors, all of that's looking good. Let's create a legend. And another thing that we could also print, maybe to the top within this cell, is we want to estimate the rate of convergence using the polyfit. So let's go ahead and look at that. We can take this set of code. So this should generate the plot. I'll just go ahead and maybe I'll generate the plot first. And, oh, errors left 1 not defined. Errors left underscore, what does it say I didn't do? Let's see here. Plot name errors left 1 is not defined. Oh, and I also should be using n, not ns, because that's what I used above. I found another error that it didn't even catch because I think they're the same array length. There's n. I called it n here because I was following these instructions. Errors left 1. Did I not run this? Let me try running it again. That's weird. Errors left underscore 1. And errors left underscore 1. So let's try running that again. Okay. I don't know what the deal was the first time. I thought I'd run that code. So, but maybe I ran it before I had defined the errors left 1. Now, here's an interesting thing with f of x equals x. The left and the right-hand rule, you can't really tell the difference of. Part of this is because we're plotting all the same lines, and they have the same level of accuracy for f of x equals x. In fact, they're producing the same, they just are producing the same magnitude of error, just one's an under and one's an over estimate. And the way to fix this so you can see the differences is if I'm plotting this one first, I will plot that as a solid line. And if I think that there's multiple curves that are perhaps on top of each other, you should change the other line styles so that they're like dashed or dotted so that you can see underneath. And so if I say, okay, I'm going to make a line style, remember you can do ls or line style as a word. Well, let's do dotted. I think that will be the dotted one. Yeah. So now you can, and I'm going to make things a little wider as well. So I'm going to say a line width. I'll do the LW keyword. And I'll make this like a line width of 3. I'll make this a line width of 2. So now you should be able to see more of the difference between, see right here, you can kind of, you can see the difference. There's that blue solid line, which is the left, and it's thick. And the dotted right errors are right on top of it. So you can see both. And you can look at the mid and say, what's going on with that? It's all the way down here. It's because the midpoint rule, the over and under estimates are just basically canceling each other out. So you're basically at machine epsilon. You're about as accurate as you can be. 10 to the negative 15, 10 to the negative 16, that's effectively 0 as far as the computer's concerned with the number of digits stored in the typical floating point number. So that's how you can interpret what's going on with this plot. Now, we haven't plotted the rate of convergence or stated it anywhere. I think it's nice to just, you can do it, you can print that information on the plot, but I'd say probably do it after the plot. Let's go ahead and copy it over. So we'll do our rate of convergence estimate, and we're going to do it for each one, the left, and we'll do it for the left, right, and mid. So errors left 1, and this is n again, right? Because I was using n's before, and now I'm using n for the array. I think it's the same array though, and I'm going to print the left, and I'm just going to get rid of this, and I'm going to also, I'm just going to copy and paste that code over, and you just change this to right and to mid, and then of course change to right and to mid. Now this should work. I'm fitting a line. That's why there's one that's a first order, and I'm returning the slope. So this should give me, and then of course change these. I almost didn't do that. There we go, right and mid. And what we should see is that these are first order accurate, that they converge with a slope of 1. And this is going to be maybe kind of indeterminable. It's going to be a little weird. You can't really interpret this because it's effectively converged immediately, because it's effectively giving you the exact value or almost the exact value up to like finite precision arithmetic for every n value. So if we run this, let's see what happens. Notice we get not a number because we can't really find a slope here. We're not doing anything wrong. It's just the issue of these numbers are, there's basically no error there. So there's no slope to compute. There's really no line. But we see here, these are at -1, first order. What you need to do, I don't think you need to see me do this, is, you could copy and paste this code if you're following along with what I'm doing and put it down here, and then just change all of these 1s to 2s. And then change the f of x equals x to x squared. And then compute these values. Here you should actually see now that this converges at a rate of 2. So it should be about -2. These will still be at -1. And then for the other function, if it's more complicated than a linear function, the same thing should be true. But you just have to do that for each of those. But again, it's kind of copy and paste and changing some things. I just want to give you some practice and insight and familiarity with approximating rates of convergence and interpreting what's going on. And then the last thing is for you to, of course, comment on these results. Some questions you should try to answer. You should do it in this markdown cell. This is just what renders when you have an empty markdown cell. So there's just nothing in there, so you just put your comments in here. Do it in a bullet point list, explain what's going on. Which method appears to be the most accurate, converge faster? It's the midpoint rule. Why do you think that is? It's the cancellation of over and under estimates locally on the rectangles. You can create visualizations of the approximations of integrals with a small number of rectangles to provide insight into this. You can listen to what I've talked about in the lecture notebooks. You can provide some code to show this. It's good for you to try to put it in your own words why one numerical approximation is better than another. It just helps you think about how you would phrase it and explain it to somebody else. And I'm kind of really hinting at here the idea of canceling offsetting errors within each rectangle. You can do some more research online. It's a good thing to just kind of check out. But I think in the interest of this video, we should stop here. The next video will go over the activity that's in Monte Carlo integration. Thanks for listening.